We are continuing with the multiple regression. The next topic is estimation of coefficients in multiple regression. Again, we will use ordinary least square method. So we are only generalizing actually the OLS method for a simple regression that you already saw. We wish to minimize the sum of squares so that distance between our original data and regression model is minimal. But this time we will have k plus 1 equations because we have k plus 1 coefficients starting from beta 0 and then from beta 1 to beta k. For that, we need to use matrix algebra to calculate it. So this is basic expression, basic formula. Again, we need only original data for independent variable and for dependent variable. Our example, I will use it only on the model for simple regression, but it is more or less equal if we have more than one independent variable. So we will actually transform our model into matrix. So these are our original data for dependent variable, original data for dependent variable, and also we would have some residuals in the real model. After that, beta hat, our estimates, we will calculate on the basis of this combination of matrix. First part, x prime x, we are calculating through this formula. The second part, inverse x prime x, then x prime y, and then we can enter everything in the formula for beta, and then beta will be calculated. But anyway, in our case, software will be helpful, and on the basis of the Gretel software, we will calculate the value of coefficients. So you remember that in a simple regression model, we had only one independent variable, class size or student-teacher ratio, and then we added one more variable into our model, and that is percentage of English learners. So you can see, because of positive relationship between English learners and student-teacher ratio has increased for more than 50%, and it is now not so, the influence of student-teacher ratio on test scores is not so big as it was before, because it dropped actually from -2.88 to -1.1. Okay. Let's go to the Gretel scores and then for the Gretel and to calculate it on the basis of our original data. So I will start Gretel. Data are already there. Okay. So we will open the model, ordinary squares. Test scores are dependent variable, independent variable, student-teacher ratio, and percentage of English learners. Here it is this EL dash percentage. Okay, we will mark robust standard errors and calculate the model. So here it is. Exactly the same results as we got, as you saw on our presentation. This is beta 0, beta 1, beta 2, R-square, adjusted R-square. We'll talk about it in a moment. And we see that all three coefficients are statistically significant, which actually means that class size and percentage of English learners statistically significantly influencing our test scores. On average, we can expect for an increase of 1 unit in the class size or student-teacher ratio, on average, test score will drop down by -1.1% test point. In the case of percentage of English learners, if percentage of English learners is increased by 1%, on average we can expect the test scores will be lower for -0.65 test points. Let's go back to our presentation. Okay, beside regression coefficients, we will always calculate the measures of fit, These are the same measures of it as in the case of the simple regression model, but now we have adjusted R-square. Adjusted R-square is actually a correction of original R-square because we have more than one independent variable, and you will see shortly that when we enter any new independent variable, R-square will continue to grow, and this is not good, and this is why we need to make some correction. Actually, this R-square adjusted will punish us if we add new variables in the model. Standard error is calculated on the basis of similar formula for simple model. So we actually are dividing sum of squares of residuals here or here, divided by the number of units, number of data minus number of our variables minus 1. When it comes to R-squared, the formula is the same, so explain sum of squares is divided by total sum of squares. Often R-square is used to assess if another variable should be added in the model. Well, it is not the best way of using R-square. It gives us some information, but it is we cannot exclude the logic when we are entering some new variables in the model. We must think if it's really in the connection with our dependent variable or not. Problem is that R-square will always goes up with some added variables, even if you add some variable which obviously doesn't have any connection with dependent variable. For example, if we have the model with two dependent variables, we will have certain size of R-square. Let's call it R-square 1. Then, if we add some new variable, literally any variable, we will get R-square 2, and R-square 2 will be equal or larger than R-square 1, even if new variable doesn't have any connection with our dependent variable. For example, if we put, in our example of test scores, if we put the parking space in front of school as independent variable, R-square 2 will be larger than R-square 1. This is why we need to make a correction of our coefficient of determination R-square. So this is the correction. Actually, we are this part here is a correction. So we are actually reducing the size of original R-square. And when you are making the report in your papers, then you need to comment on R-square adjusted, not on the original value of R-square. Only in the case of simple linear model, you have one independent variable, then you comment on any of these two indicators. So in our example of simple regression, we had R-square of 0.051. When we added English learners in the model, original R-square was 0.426, but corrected is a little bit lower, 0.424. And we can see that we have improved our model significantly because R-square is now much higher than R-square in the simple model, which is good. And our standard error is lower in comparison with the simple model. But anyway, the true value of R-square should be this. So 42.4% of variation in test scores is explained by variations of student-teacher ratio and percentage of English learners. Let's go to our example. So here it is, original R-square here and adjusted R-square here, 0.424. So this is the one that you need to comment. And also standard error of regression, which shows us that average distance of original data from regression model, from regression plane in this case, is 14.46 test points. So standard error is always expressed in the units of measure of our dependent variable y. In this case, these are test scores. Let's go back to presentation. Let's go back a little bit to theoretical part. So what are the assumptions that our model needs to satisfy in order to be good model, in order to be blue? So first three assumptions are actually the same as in the case of simple regression model. So the first one is that conditional distribution of UI of our residuals for given values of independent variable x, in this case more than 1x, needs to have a mean average value of 0. This could be evaluated if errors are correlated with some of the x's. So if you have some omitted variable, then you will have relationship of UI with some of the x's, with some of the independent variables. Second assumptions about independently and identically distributed data. So we need to have some kind of randomization in our data in order to get a true model. So for example, in our when it comes to districts of California, you need to put out of all the districts in California, you cannot put in your model only the richest districts or only the poorest districts. You need to have the same variations in your example as in the true population that you have. So the same percentage of rich districts and poor districts, same percentage of districts with higher percentage of immigrants and lower percentage of immigrants, and so on. Okay. Third assumption, that large outliers are unlikely. It is already explained. In order to hold for consistency, we need to have this case without large outliers in order to obtain normal approximation, normal distribution of our data. The new assumption in the multivariate model is that there cannot be the case of perfect multicollinearity in our data, that two of the variables or more than two of our independent variables cannot be perfectly correlated. What does that mean? So if we have a model with three independent variables, and for example, if we can express x2 from the variable x3, we have a perfect multicollinearity between these two variables. For example, if for x3, if the value is 2, we are getting for x2 4. For every value of x3, let's say 5, we are getting 10 for x2. So we have perfect multicollinearity. We know the answer is for the x2 if we know the value of x3. Then we have the perfect multicollinearity. And we need to avoid that. For example, if you have the sales as our dependent variable, and on the other side, you're looking at the prices in euros, in dollars, it is obvious that you have perfect multicollinearity between these two independent variables, because if you know the exchange course, you know the value of euros if you have dollars as a price. So it is the case of perfect multicollinearity. The recipe is to exclude one of them from the model. Because if we have perfect multicollinearity, there is no unique movement of the variables. So euros don't have unique movement if we have the movement of dollars. The explanation is also the following. If we don't know, if we have the 100% influence of one variable to the other, if we have perfect multicollinearity, then we cannot assign the influence of any of these two variables to dependent variable. We don't know who is influencing more and which variable is influencing more, which variable is influencing less. It is like when you ask yourself who is talking from the crowd. You can hear a voice, but you cannot assign to the person who is really the one who is talking. So we are actually having the mixture or influence of two variables, and we cannot decide the real influence of x2 or x3 on yi. What is the solution? I already told you, to drop one of them out from the model. Later on, we will talk about imperfect multicollinearity, when two variables, two or more than two variables, are correlated, but not perfectly. Now we will talk about the distribution of OLS estimators in multiple regression from beta 0 hat to beta k hat. So we are expecting that they are unbiased and consistent if 4 assumptions holds, and their joint distribution should be good, well approximated by normal distribution. We are expecting that they have a normal distribution, which is actually in line with central limit theorem. Central limit theorem is a set of rules explaining that with the growth of your sample, we are approaching actually normal distribution. Like I told you already in the simple regression model, that in large samples, beta 1 hat, will have normal distribution even if y independent variable doesn't have normal distribution, but only under the condition that n goes to infinity, that n is large, minimum 100 units in your sample. Now let's go back to multicollinearity. So we have a model with 3 independent variables, x1, x2, and x3. Now let's say that we have perfect multicollinearity, like you've seen already before, that x2 is actually linear with in perfect collinearity with x3, because for every value x of x3, we know the true value of x2. The case of imperfect multicollinearity is actually when you have some error that for a given value of x3, we will not get always the same value of x2. So in the first case, if we have, for example, 3 times for x3, we have value 2, always the answer will be 4. 3 times 4 for x2. But in this second case, if we have 3 times value 2, for example, in our data, sometimes the value of x2 will be 4, sometimes 5, sometimes 3. So this is why we have some error, some variations in our residuals in this case. And then we have imperfect multicollinearity, and this is something that is allowed. Then you need to have both of those variables in the model. Actually, in this case, or on multivariate models, you can have on the right hand side more than one independent variable. So one variable can be actually the combination of more than one other independent variables. So this is the case of perfect multicollinearity here, and this is the case of imperfect multicollinearity. So we've plotted the values of 2 independent variables, and x2 is influencing x1. So the raw data are these dots here, and we have a model. So we know for 100% for a certain value of x2 what will be the value of x1. But in the case of imperfect multicollinearity, this is not the case. We can say on average what is the relationship between x2 and x1, but actually real data have some variations. So for certain value of x2, for example, here, we can get in reality different values of x1. So this is the case of imperfect multicollinearity. When it comes to imperfect multicollinearity, like I said, we have some error in our data, some variations, and then we should keep both variables in the model. For example, in our case, we have student-teacher ratio in English learners. And let's add new variable, percentage of first generation. So percentage of immigrants that are first generation coming into certain districts in California. Obviously, this variable is related to percentage of English learners because these are also immigrants. So maybe in some districts it will be actually the same number because all the immigrants are actually first generation coming and becoming also English learners. Therefore, it is likely that EL and first are highly correlated, but we have imperfect collinearity because some of those immigrants which are first generation will not come to the university, and then we will have different numbers for English learners, percentage of English learners and percentage of first generation immigrants. But anyway, it is those two variables are correlated. What are the consequences? Well, if we have imperfect multicollinearity in our model, estimates are still unbiased and consistent, which is good. Now, we will be still on the true value of beta 1 in the population when we calculate the value of beta 1 hat. And it will be consistent, which means if our sample is growing, we will actually travel, let's say, we will obtain the similar values of beta 1 hat and going to the true value of beta 1 in the population. The problem is standard error of our estimates of our coefficients beta hat, because it will go up, it will be higher. So in our example, if x2 and x3 are imperfectly correlated, what will happen? That standard error for beta 2 will go up, it will be higher. Also for beta 3 it will be higher, because the software cannot decide which of these two variables contributes more to the explanation of our dependent variable. And because of that insecurity, the standard error, the variation, the estimate of variation of beta 2 hat in population will be higher. Standard error will be higher. This causes that t statistics goes down, that it is because standard error is high. Then if we divide this with standard error, t statistics will be lower, which means that we will, when we are testing beta coefficients, that we will accept the null hypothesis that beta 2, for example, in this case, is equal to 0 in population, but actually it is not. It is actually statistically significant. So this is actually the danger if you have multicollinearity, that our standard errors are becoming larger and now testing a hypothesis is not reliable. We cannot just drop it out of the model, one of these two variables, because then we will have a problem of omitted variable bias. There are some other solutions that we will see later on. But one of the best solutions is to get more data and then to solve for a problem. So when it comes to omitted variable bias in a multiple regression, it occurs when actually you know omitted variable is correlated with any of already involved independent variables in the model, and when omitted variables helps to explain yi helps to explain dependent variable. In the case of omitted variable, estimates are biased and inconsistent. So this is much bigger problem than the problem of multicollinearity actually. Now let's talk a little bit more general about the model specification. How do you define the list of variables that you want to include in your model? What variables to include? So choose a core set of variables based upon the expert judgment, economic theory, and knowledge how data were collected. So you need to read the literature about the problem that you want to explore and to rely upon the previous analysis that were in scientific literature. That will make your base specification. So first list of variables that you want to include in the model, under the condition also that you are able to collect all the data that are necessary. So out of that, you will make, on the other side, you will make the list of candidate variables, some other variables that you want to test if they can be included in the model. And then check for the robustness, putting in and out candidate variable and look at the changes in betas and R-squares. So you will actually, some kind of a dance, let's put one variable, let's take the other out, let's put two more variables in the model, let's take two more variables out of the model. So you need to make different combinations in your model in order to check the variations in your betas and R-square in order to find the right model. And the next topic, and the last topic in this presentation, is how you interpret R-square and R-square adjusted in practice. A high R-square means that regressors are good at predicting y. This is a fact. But there are 4 points. An increase in R-square does not mean that added variable is statistically significant. So you already saw that if you put any variable in your model, your R-square will increase. So it doesn't mean that that new variable is really statistically significant. You need to check other elements in your model in order to be sure about the significance of the new variable. Second, a high R-square does not mean that regressors are true cause of Y. For example, if you have umbrellas and rain, if umbrellas are independent variable X and rain is dependent variable Y, they are highly correlated, but anyway, it doesn't mean that a number of umbrellas can influence that they can cause the rain. Also, the second example that you already saw in our class size, then parking lots doesn't have any influence in test scores, although maybe if you put them in the model and you get statistically significant coefficients, so it doesn't mean that there is true relationship between these two variables. You need to think logically and understand that size of parking lot doesn't have any connection with the results on the test scores. Third, a high R-square doesn't mean that we are free of omitted variable bias. So even if you have very high R-square, for example, 0.89, it doesn't mean that you didn't omit some other important variable. And fourth, a high R-square does not mean that we have most appropriate set of regressors, which is actually related to the previous fact. So you must be very, very careful while exploring the list of the variables or your specification for developing the model. A low R-square doesn't mean that we do not have most appropriate set of regressors because of high variance also. This is the end of presentation.